Hello everyone. It's great to see you guys joining in early. Please stay tuned. We'll be starting shortly. So hello everyone, welcome to another session in the DataHour series. We'll be starting in 5 minutes. So till then, we'll get to know each other in the chat section. Also, I'm going to launch a poll. I would request every one of you to kindly fill in. Hi Samuel. Hi David. Hello. Hello Emily. Hi Kundan. So also please post where are you from. So Samuel from Nigeria. I have launched a poll, guys. Please kindly participate. Hi Dora. Good evening, Ankit. So please stay tuned. We'll start in a few minutes. So, hello and welcome everyone to another session in the DataHour series. We are also thrilled to be here with you this evening for a session full of action-packed learning. I am Tamil Selvan Murugesan, part of the data science team at Analytics Vidhya, and I will be the moderator for this session. So, for those who have joined us for the first time, let me give you a brief introduction to the DataHour sessions. The DataHour is a series of webinars conducted by Analytics Vidhya and led by top industry experts. It is a fun way to understand the concepts of data science from the leading players in the data tech domain. And also, as the name suggests, it's 1 hour dedicated to data. We are hopeful that these sessions are going to be a great source of enrichment and value adding for our community members. Now, onto our session today, which is designing an end-to-end neural search pipeline with similarity learning. The good old world of search engines had been dominated by keyword-based search for ages, but it has reached its limits. Neural embeddings allow us to explore completely new areas, including visual and audio search. Thanks to publicly available pre-trained models, everybody can reuse a particular network for their tasks, and that no longer requires dozens of GPUs or labeling millions of data points. Similarity learning is a modern approach that lowers the data requirements while keeping great performance. So in this data hour, Mr. Kacper is going to describe the basics and present how to create an end-to-end pipeline using specialized tools. I hope you are also excited to attend this data hour with us. So before we kick things off and I hand it over to speaker, a quick recap of the housekeeping items. We are recording the session and we'll make the recording available in a few days on our YouTube channel. Please use the Q&A section for asking any questions you might have during the session, and we'll do our best to answer them as the data hour progresses or towards the end. Also, we will share a poll about the feedback of the session towards the end, which I request you all to kindly fill up. So now onto our speaker. In this session of data hour, we have Mr. Kacper Lukwaski with us. Kacper Lukwaski is a developer advocate at Quadrant, an open source neural search engine. His broad experience is mostly related to data engineering, machine learning, and software design. He has been actively contributing to the discussion on artificial intelligence by conducting lectures and workshops locally and internationally. Recently, he's been focusing on similarity learning and vector search. So over to you, sir. The virtual stage is all yours.
Thank you very much. I'm really glad to be here and hope you will find this session valuable, because similarity learning is something that surprised me quite a lot, because I wasn't really aware of its powerful mechanism and things that might be easily achieved compared to these traditional methods. And hopefully I will manage to show you how you could also utilize it for your own purposes. So basically, let me just share the screen. And go directly to the slides, because I believe the topic is quite important and we have a limited time. So just not to spend too much on the introduction itself. Yeah, as already said, we are going to be talking about neural search pipeline created with similarity learning. And we are going to use open source projects which are developed by Quadrant, the company that I work for. A few words about myself. As already mentioned, I'm a developer advocate at Quadrant. We are making a state-of-the-art neural search open source engine. And if you want to keep in touch, these are my social channels. Please feel free to reach me anytime. Would be happy to discuss anything related to similarity learning or any of our projects one-to-one, because I believe some of you may just find it interesting and exciting as I do. And before we start with the similarity learning, I would like to make a brief look at the history of search in any kind of applications. Well, in computer science, we had some different attempts which were mostly related to the limits that we had for our the limits of the computational power we had over time. And right now there is a great new wave of search which is based on neural networks. But before we start with those neural networks and how they could be applied for search operations, we are going to briefly describe some initial attempts of how to make search even possible. Well, I believe most of us are pretty familiar with the SQL-like databases, and at the good old times, the only actually, or the only so broadly available possibility to perform any kind of search was to set up a Postgre or MySQL database and use the text search capabilities of those tools. However, that worked only if we had a text with the exact phrase that was available in the collection of text that we have created. Of course, there are some attempts to normalize the text and queries that we sent to the database, but at the end of the day, we still had the exact query matching. And behind the scene, this algorithm could use like a naive substring matching or some more sophisticated full text indexes, but the problem stayed the same. And one important thing is that we actually had to run every single query against every single entry in our database with this like operator, or use some full text engines, but that didn't work that well. Then some new methods came into the game, and they were mostly based on some sparse vectors. As I have already told, this exact phrase matching worked only if we knew the data that we were searching on, and that was limited to some simple queries only, because even the order of the words in our query could affect the results. And sparse vectors based methods actually solved some of those issues and allowed us to perform the search in a bit better way. And algorithms like BM25 were the state of the art in the key. They still do, but they were state of the art in the search in general, but mostly focused on text. And what is the idea behind the sparse vectors? Actually, we convert every single text to some kind of vector representation, but those vectors tend to be quite long. And let's imagine we have a huge collection of text, so-called corpus or corpora, and we just extract all the possible words in all the text that we have. And by doing that, we create a dictionary. And this dictionary is like a collection of all the unique words that may occur within our text. That approach has several drawbacks. For example, that assumes that the dictionary is not going to be changed at all. So we have our training set as usual. We build this dictionary and then just assume that nothing's gonna change and the language will stay the same for ages. That rarely works, but that allowed us to move a bit forward with the search, because the idea behind that is that every single text, once we have this dictionary created, every single word from this dictionary will have a specific index. So we can just convert every single text to a vector that will be representing a list of words that occurred within the text. Basically, this is like a description of the text, of the content of a particular text, but that doesn't necessarily work with all the possible cases. Let's imagine we have a negative sentence, and if we just encode it as in the basic scenario, we just encode it in a back of words manner. So if the word occurs within the text, the corresponding position will get 1, or we will just count the number of occurrences of a particular word. But if we have a negative sentence, then a position with related to a word no will get one at this dimension, and actually the representation, the vector representation, will be almost the same like the positive sentence, and that's an issue. However, we were using these methods for quite a long time, and they work pretty well. There are, of course, some ways to overcome different issues, because these dictionaries tend to be quite big. So the vectors are also huge, and most of the positions have zeros. So that's why we started using sparse vectors representation, because only some of the positions were non-zero, and that simplified storing them a lot. And there are also some other issues with that, like those out of dictionary words that may occur. And we were solving that by data normalization, like lemmatizing or stemming, providing a list of synonyms, but still the data dimensionality is enormous. And it may go even higher if we decide to use n-grams. And one thing that is worth noting is that every single permutation of the same words will keep the same representation. So order of the words doesn't really matter. And if you would like to find some example of how the query can be modified for the human to be completely different and to have the same representation, that is also fairly easy. So we were dealing with that quite a lot. But that was the only option that we had at this point of time. But there are also some other issues that we have with these old ways of solving search. They are mostly focused on texts. So if we work with anything that is beyond text, like images, videos, or audio data, or actually any kind of any data type you can imagine, then either we need to find a way to convert it into text and then perform the search using those text-based methods, or we actually couldn't really use them for the search purposes. But this time has come to an end. I mean, we do not longer want to query only our textual databases, textual data sets, but also we would also like to start using our unstructured data that we have. We actually got all used to visual search and using tools like Google Lens, and we would probably also want to perform the same process for our own applications, especially if we work in industries that produce a lot of non-textual and unstructured data. And even the greatest BM25 model cannot work on images as long as we do not convert them to some kind of dictionary or features. But this feature engineering might be quite tough and not worth the effort. And actually, none of the methods that we mentioned so far was able to capture those features of the unstructured data, and that's where neural networks come to the rescue. Just as a short recap, neural networks designed to solve classification problems are typically built in a similar way. We have a bunch of layers which are stacked on each other. And the last layer is some kind of activation function like softmax that produces a probability distribution over all of the classes. And the highest value in the final representation wins. So this dimension is just related to a specific class name, and this class name or this class is being produced as a most probable class for given example. So the highest score wins. And this is some kind of proxy for the probability as well. So this is a cool feature, because we can directly derive how model is sure about its prediction. And again, each neural network is a series of stacked operations, some kind of multiplications and non-linear transformations. And that means we can actually put some data at the network input and then see what are the values, what are the activations of every single neuron or every single layer of the created network, and actually look at it as if it was like a mathematical vector, similar to those sparse vector representations, but here of much lower dimensionality. And this temporal state of a particular layer started to be used as some kind of different representation of given input. So the idea in a nutshell is that with every another layer of a created neural network, we should be able to capture some more sophisticated patterns in the data that we put as an input. So if we just take one of those layers and treat it as a vector, we can have a different representation. Let's say it's like a compressed version of the original input, and we call that temporal state of the network an embedding. And this is an important part, because we can start using our good old classification neural networks to some kind of a different task. This is exactly the same network. We are just coming back to the previous example when we designed the classification neural network. If we simply detach the output layer, the one with probabilities, we can start extracting the state of the previous layer and treat it as some kind of representation of this input data. And this is often called encoding or embedding. And that should capture the properties of the input objects. And thanks to the fixed dimensionality, we can also start comparing those vectors and use the distance between two different embeddings to determine if they describe a similar object. The thing is that here we can put image or audio or actually anything that has non-fixed dimensionality, so a different resolution of an image, but still our network will produce a vector of the same dimensionality every single time we put anything as an input. So that makes everything comparable to each other. And the most important part is that we don't necessarily need to train our models from scratch. Here we had a neural network designed to solve classification, but if we just remove the last layer, the output layer, we can just treat the state of the previous one as some sort of desired output. And since there are already hundreds or thousands of pre-trained models available online, and if you use Hugging Face Hub, there is a lot of models that you can just take out of the box and start using right away. So unless your data is of non-standard type, we should be able to find an existing network and start producing the embeddings without much effort. And those embeddings should already start capturing some of the regularities in the data. And what is cool about that approach is that we don't necessarily need to train this network at all. If we take any pre-trained model, it should already have some weights, typically trained on quite a huge data set. So we don't necessarily need to reproduce the same process, but we can just start using something that was trained on a hardware that we could probably we cannot afford on our own. And that's a huge game changer for those companies or just individuals who couldn't really afford spending thousands of dollars on some cloud resources. And that is really cool, because that's a way to democratize this artificial intelligence, because actually everybody can start using those huge models right away. But there is another thing. If we take a network that was trained on, let's say, ImageNet, which is quite a popular data set, chances are it won't be able to be directly used on, let's say, medical images. However, those first layers of the network should already capture those low-level traits of the pictures, and they are pretty universal. And those layers should already have some information about the shapes and about some visual perception in general. And since the initial goal was to classify the images, because ImageNet is a data set built for classification, the top layers will be mostly focused on classification. And if we wanted to use them to compare embeddings, they may require some more training just to fit our own data set a little bit more. So when we are switching to a different domain, those embeddings might not be not be at their best. So some additional training is quite important. However, that doesn't necessarily mean we need to train a whole network. Here, I oversimplify things. Those pre-trained visual models, for example, have many more layers than just 3 hidden layers, but there are dozens or hundreds of layers with millions of parameters to be trained. So you can imagine that changing those weights in every single layer will cost us a bit more than we could want to, and that's not the easiest way, because that will also require a lot of computational power and a lot of time that we maybe cannot afford. So instead of using those original embeddings created by the network, we could try to just attach some new layers at the end of the network, at the output of it, and train the network to slightly adjust the weights only in that part of the network, on those last layers. So then those embeddings will be just closer to each other than they originally were. And the idea is that if there were 2 objects which are similar in some way, we need to know they are similar in some way. Their embeddings should be close to each other. And the approach that we try to promote is to freeze this original part of the network, freeze this huge pre-trained model that we found, and just update the weights at the attached head layer. So instead of adjusting millions of weights, millions of parameters of the network, we can just adjust, thousands, what may be done in a reasonable amount of time. So our training is no longer is not going to longer look like previously, but those layers will be just frozen, and we will be training the missing part of the network. And here there are dozens or hundreds of layers stacked on each other. And that seems reasonable. However, there is unfortunately one major problem, because in classification, we actually knew the ground truth for our training set. So let's say if I put this image, I knew that a specific class should be assigned to it. So that was fairly easy. But it's not the case if we want to generate embeddings. We do not know the perfect embedding for any given signal. And that's where similarity learning, aka metric learning, uses a different strategy. Because instead of providing the targets for the input samples, we provide the network with some similarity-related information. In other words, we say which objects are similar to each other and let the network select the embeddings in a way that similar points will be represented in a similar way, without telling the exact coordinates. I really like this analogy, because if you just look at this vector, well, let's say if it was just reduced to 2 dimensions, that could be thought to be like some kind of geolocation. So latitude and longitude of the point in some kind of space. But here we just extended the space. It is just higher dimensional, but still this is some kind of location of the point in that space. So it's a bit easier to imagine how it should work. Okay, but we are not going to tell the exact coordinates, but we are going to create our set in a different way. The dataset for similarity learning is built differently than for the other problems. However, if we fine-tune our existing model, the goal is not to start from scratch, but just slightly adjust the original embeddings so they're closer to each other. So we built, there are like two strategies of how we can build our data sets. The first one is to provide groups of similar objects. And that's the easiest way, because we can just, like in classification, we can just select a group of input samples that we have and tell the model that they should be close to each other because they belong to the same group. And this is fairly easy. Here we have some chairs, some flowers, some cars. So we are pretty sure that they should be put close to each other. This ones as well. But all those three groups should be rather far away in that space that we are going to be modeling. And that's the easiest way, because we just provide an information of belonging to a specific group. But there is also another scenario where we can provide a pairs of samples. I mean, we can provide an information that there is a pair of examples, let's say those two flowers. And with this pair of examples, we also provide a similarity measure. So a number from 0 to 1, describing how similar those objects are. So 1 means like a perfect match, and 0, like they are not that close to each other. And basically the idea behind that is, if we want to create those embeddings in a case where we have some sort of similarity measure given from the outside. Let's say if I wanted to rate some movies on IMDb, then I will rate them from 0 to 10, I believe. And this kind of information may be thought to be like a proxy for the similarity. And if we wanted to create a recommendation system, that should work pretty well, because we would already have that information. But in a real case scenario, if we just start with a specific data set, that's not necessarily always possible. So this strategy of using groups is way easier. And there is also another idea. Because our network already had some embeddings which were just not working that well as we would expect them, we don't necessarily need to provide like millions of examples to train such network. The idea behind similarity learning is to provide just a little data set that anybody can annotate within, let's say, a day or even few hours, like hundreds of examples, because we are not going to be starting from scratch. We are going to be adjusting those weights just a little bit. So coming back to this example, just by looking at the numbers, the idea is not to like start from some random points, but if we just compare those dimensions one by one, you can see that there is just a slight difference between those values at each position, because that was the goal from the very beginning. We don't want to lose that information that was created by a whole network, the original network. We just want to make some tweaks to make it spread in a better way, so something that would expect to provide us. So just a little data might be enough to fine-tune the existing network. And under the hood, this is going to be using some sort of loss function, which is designed for similarity learning. And one of the obvious choices is to use triplet loss. And here is the image that describes the idea a little bit. So in the original network, we had those anchor and some negative and positive sample. And negative sample, the one that is not similar to our anchor, was just closer than the positive one. So the goal of triplet loss is to provide those triplets, so anchor, negative, and positive example, so the network can just move those embeddings, move those points in the output space a little bit, so they are so the positive example is closer to the anchor than the negative one, and that happens through a few epochs. But okay, that was just a description of what similarity learning is about. But we can start doing that in practice. And I also prepared an example of how to do it using the tools that we work on. And we are just going to go step by step through the whole process. Let me then just switch to the notebook that I prepared. This notebook is going to be shared with you. So let's just start with the data set that we are going to be using. Basically, there is an open Stanford CARS data set that is built from thousands of images from 196 classes. It is split into training and testing subsets, but that doesn't really matter because we are going to merge them together and then split it again. So at the end, we will have a training and test set containing all the examples from like 50% of the classes. Both will have different classes. So our created model will be able to be tested with some classes that it hasn't seen throughout the training process. And we are going to be using Quaterion. Quaterion is a framework, a similarity learning framework that we create at Quadrant. And it is designed in order to simplify designing those metric learning or similarity learning pipelines. There are several issues that you may typically face while working with similarity learning, and we try to make the whole process easier for you. Okay, so we are going to start with some necessary imports as usual. There are some things that we need to import. One thing worth noting is that Quaterion is a PyTorch Lightning based tool. So if you are familiar with PyTorch or PyTorch Lightning, or already use any of those frameworks in your case, then you can simply just add Quaterion to your code base and start using it and start training the models in almost exactly the same way like you did before. And well, this is just some introduction. We need to import some things, and we are going to be declaring some building blocks of similarity learning pipeline, which are quite similar. First of all, we need to create a data set, which is like a way of exposing the data. And in our case, the data samples will be represented as groups. So this is the easier strategy. We are going to be using groups. So each object for our training set will be will have the group assigned to it, and Quaterion will automatically use them for the loss function to just move those points in the space. This is fairly simple. We just need to provide two methods here to return the size of the data set, and another one for getting the item with a corresponding index. And as you may see, we are just producing similarity group samples, which is Quaterion representation of those points, and each point is just extracted from the original data set, which is like a collection of images with this label, group label, attached to, as another parameter. And that's basically it. We also have some kind of transformation of those images. That's quite a typical way, because those images are typically normalized before being put into the network. And that's it. That was quite simple. And if you are familiar with PyTorch, that was nothing easy for you. And another thing, we are also going to create some helper functions. So those functions are going to create those data sets, training and test data sets, and corresponding data loaders. So there is also nothing really different comparing to PyTorch Lightning. Here we have some transformations being declared because on ImageNet, the images from ImageNet are also normalized before being put into this pre-trained model that we are going to use. So we need to recreate the whole process as well. So our images are just normalized to a specific input size and then normalized, have the colors normalized. And then we just load the Stanford cars data set, which is available in one of the libraries that we use, and select randomly the categories to be used as a training set, and the rest will be used as a test set. Where actually there is just a simple processing, but at the end of this function, we are just producing two data sets, one training set and one test set with the syntax transformation being applied. So this is very easy. We have just created two separate training and test sets, so nothing really new, except for this cars data set and the way that those samples are being represented. Okay, and another function for the data loaders. So taking the data sets and returning the data loaders using those data sets under the hood with a specific batch size. Okay, and the encoder. Encoder is a name that we use to define this part of the network that produces the embeddings. So some kind of transformation from the original data into mathematical vectors, embeddings or codings. And Quaternion requires you to provide this encoder and then attach a head layer to it that we further fine-tune. And we are going to be using ResNet network that was trained on ImageNet. That's why we had those transformation applied as in the same way like the ImageNet does. As you may see, there are not that many cars. Here there are just a few examples, but there are also some animals, people, places, where actually items, actually anything. And in our case, we were purely focusing on cars. So even though those embeddings might be useful as they are probably not capturing the differences between different cars, but just focusing on a item being presented on the image itself. So we just need to fine tune them. This is quite obvious that our data sets are a bit different, and the results could be improved if we just adjust those weights a bit more. So we are going to create another thing, which is this encoder, another import that might be required, and we are going to define this cars encoder. So that takes this original encoder model and defines the embedding size. So we are going to be using the last dimension from the ResNet model. So this has already a fixed dimensionality, so we can just declare it as it is. And we define this is part of Quaternion. We define it to be non-trainable because trainable property will return false. Under the hood, once we launch the training of that model, that part of the network, this original encoder, ResNet that we took, won't be trained at all. Also, another thing that we need to provide is the embedding size. And as usual, we need to have a forward pass of the network that will be just creating those original embeddings and returning them, and methods to save and load the model once it's stored on the disk. And that's fairly it. Okay, and the third component which is required is the model that will be built from this encoder and our head layers. And PyTorch Lightning has its own Lightning module, which is in turn a subclass of module from PyTorch. And in Quaterion, we need to define trainable model, which is also compatible with PyTorch Lightning with those additional methods. But all the rest stays the same. It's fairly simple to switch from PyTorch Lightning to Quaterion, because that's really using a similar interfaces. Tried to keep it as similar as possible. Another bunch of imports that might be required, and here is the model. Also fairly easy because we already have this encoded created. So we need to define a learning rate for the model and the mining strategy. We'll describe it a little bit more in a second. And then we need to configure these encoders. So we load this original ResNet model with pre-trained weights from Torch Vision, and then change the fully connected, that's the last layer, to be like identity. So it's not longer going to perform the classification anymore, but instead that will just reproduce the input without making any changes. So this pre-trained encoder is going to be modeled that won't be producing like a probability distribution over classes, but instead some sort of internal representation of the previous layer, and that's it. And configure encoders was the first method that we had to provide for the trainable model. Configure head is another thing. Here we are going to be using skip connection head. Just in a few words, skip connections allows us to reuse those original embeddings together with those newly created weights, so we do not fall into the trap of catastrophic forgetting. Because if you remember, I told that already, but we are not going to start the training from scratch and want our embeddings to be completely different. We just want to slightly adjust them, and the skip connection head allows us to do it easily. I may just put a link to an article from our documentation that describes that clearly. But that's a good way to start using that for the cases when we just want to slightly adapt the original embeddings. Of course, we can provide the dropout. And another thing is the loss function that we are going to be using, triplet loss. So something that we have already covered. So our examples are closer to each other with margins selected, and optimizers, but this is fairly the same like we did for any PyTorch or PyTorch Lightning mode network. We also need to configure caches. Well, actually, that's one of the things that is like the game changer in Quaterion. In the example that I showed before, this example of the network that was having this encoder that was intended to be frozen, there is one thing that is really important, because if we freeze the encoder, then it becomes deterministic. So if we put a specific example, it will always produce the same embedding. And we actually started thinking like, why the hell we need to put those images for every single epoch, then calculate like millions of operations to produce the same embedding? There is a huge room for improvement, because if we just make a cache storing all those embeddings instead of loading the images from the disk, so there is some I/O included that will slow your process a bit. We just thought that, well, that would be cool to have those embeddings put directly to the device that is going to be performing this training, and instead of loading them back and forth in every single epoch, we can just reuse them every single time, just perform the load operation once, and then omit those quite heavy computations of this ResNet or any different pre-trained network that we select. And we did that. Actually, that is a fairly simple idea that I really loved when I saw that for the first time. We just need to configure the cache mechanism of Quaterion by providing a specific method. And here we decided that this cache is going to be like automatically chosen. I mean, you can select GPU or CPU, but if you just provide auto, then it will automatically put those images to the device that will be performing that training. Because that's also quite cool about this cache mechanism, because right now, if we no longer need to perform those heavy computations, which are typically based on some heavy matrix multiplications, that's why we perform them on GPUs, we are just like adjusting those weights in a small fraction of the original of the number of weights, and that doesn't necessarily require having like a high-end GPU to perform those computations. There is no like bunch of matrices to be multiplicated, but this is like a very simple transformation at the end of the day from these original embeddings of the pre-trained network to that embedding that we want to have. And that's why if you use Quaterion, you no longer need to use a high-end GPU. Of course, you can do it. We support GPUs, but if you want to like experiment on your laptop, then it's also possible, and that will be very, very fast comparing to training a whole network again. So that's cool. We also need to provide some metrics. So retrieval R precision was the choice here, but there are several other metrics that you can also use in that case. But that's it. That is fairly simple. We have just declared a whole model that we can train right away. Okay, so that's high time for the training. We have all those three building blocks. We have the data set, we have the encoder, and we have this trainable model that we can now put together and start the training phase. We will do it in almost the same way like we would do for any PyTorch model. Quaterion provides a utility method to feed an existing model with a provider instance of a trainer class that you are probably quite familiar with. Okay, so let's start with some imports that might be useful and the training method. So just step by step, we first of all create our model with a specific learning rate and mining strategy. We then create the data loaders, which are necessary to be able to get those images from the disk where they will be downloaded. We decided to use early stopping, and then we just need to declare the trainer as usual in PyTorch Lightning. That will be trained on GPUs if any of them is available with a specific maximum number of epochs, some callbacks, disable checkpointing, and log in every single step. And then and the only change for the comparing to the standard training of PyTorch Lightning models, we just call Quaterion feed method, providing the model, the trainer, train data loader, and validation data loader. And we can just save model after being fed to a specific directory, and also return a model if we wanted to use it after. And here we can just train the model and assign it to a specific variable with those specified parameters. And this is fairly simple. We can do it in almost the same way like we would do for any other network. But thanks for this caching mechanism, we are going to be launching that even on a small data set and even on a CPU without having to pay lots of money for renting the cloud GPUs. And here are the results. This is the comparison of these original embeddings with those fine-tuned ones. So the pipeline that we have created allowed us to fine-tune this original model, original ResNet based model, to a not necessarily completely new, but to a different domain, I have to say, because previously we were looking at different kinds of images, different kinds of items, But here we are solely focusing on cars. And as you may see, if we queried this original model with this specific car, I'm not sure about the brand, but however, it was returning some cars, but honestly, I'm not really sure what those two have in common. They're quite different. Even the shape is different, but yeah, it was just returning some examples, still cars, but that's how this data set is built, but not very similar. But if we just fine-tuned our model, here we have the same car. Even the driver is probably the same. Just by looking at the example, it seems like this is the same person, but this is the same car with a different color. So this fine-tuned network was able to capture some more subtle details of those original images. And that is cool. That is cool because we reused the existing networks. That's not necessarily what I like about similarity learning is that that allows us to reuse something that somebody was training for quite a long time. Well, I have never tried to do that, but I bet I won't be able to train ResNet on my laptop. But all those vision-related problems will be kind of similar. Yeah? Like the shapes won't be completely different. There is like a limited variety of shapes that may occur on images at the very low level. So if we have already trained the network, there is no clue to like retrain it again for every single experiment we want to perform. This similarity learning is way better just because it allows you to experiment quickly. You can, well, previously, if you were to train this network, that will take you like weeks or even months to perform the network from end to end. But if you just train a single layer, then you can run several different experiments within a single day. I know that all the data scientists like to wait because you have some free time, your work time. So that's really cool. But at the end of the day, we need to be efficient. And similarity learning is a way to make our work more efficient. Way more efficient than it was before. And also from the environmental perspective, training such a huge network will cost us money, energy, and definitely it's not like the greeniest way of performing those experiments. But with similarity learning, we are reducing the time spent on the training significantly from weeks to minutes or hours. So definitely that's a way better for us, better for environment way of training the networks, unless we are working in a completely different data type that was never trained, that none of the existing pre-trained models was never trained on. But that's really cool, and that's why I'm really excited about similarity learning and applying that for different things. And if you would like to reproduce this this model training, the code is available on our GitHub. You can just download it. This is one of the examples of using Quaterion, but that may be easily used as some kind of baseline if you have a different data set, because the only thing that you will have to change is the way you load your visual data. But if you want to, let's say, recognize not cars, but I don't know, flowers, people, whatever, you can just change the data set and keep all the rest the same. And hopefully that is going to work also for your case. But that's not enough. Right now, if I computed all the embeddings for, let's say, thousands of examples from my data set, I could try to find some similar examples by comparing the distance between my query. Let's say I have a image of a specific car I would like to buy. And if I wanted to find this car, I would need to compare the distance to every single example in our data set. So that will scale linearly. That will be like a full scan in the relational SQL like database. So definitely that won't be like the best way to do it. and we need to like, well, of course, if we have like dozens of examples, then we don't really need to worry. That will work out of the box. That will be fairly simple. But let's say if we have like thousands or millions of examples, then things will start to slow down. Well, creating these embeddings is quite a heavy process. Like calculating the embeddings in a network that is built from dozens or hundreds of layers will take some time. And if we have another bottleneck, like performing a full scan, like full scan in a relational databases, then we will have two problems instead of just one. So the thing is here that if we calculate the distance to all the examples that we have in our data set, then we some sort of create a KNN classifier. I hope you agree with me. This is basically the KNN classifier where we in which we just calculate the closest points in some kind of space. And I'm not sure, but I have never seen a working KNN in production that would be built on top of a huge data set. Of course, there are some examples for which people just use, I don't know, dozens of images and or just data points, and that works fair enough. But if we have like several millions or our data set changes over time, so it may grow, then KNN won't be the best solution, because that won't scale that much. However, there has been a lot of effort going on in terms of in the area of approximate nearest neighbors, which is like a related method, but that scales way better. And Quadrant, which is our main project, also open source. That is a neural search vector database. It provides the possibility to perform this approximate nearest neighbors, but in a faster way. And it exposes HTTP and gRPC interfaces, so that is fairly easy to be integrated with any stack you have. And we have some existing client libraries. A small disclaimer, we are also quite fast comparing to the competitors, because we are built on top of Rust, which is really efficient. So, well, none of the Python-based tools can offer you such a great performance. So definitely, if we want to have like an end-to-end neural search engine, we need to also think about not only about creating those embeddings in a proper way, but also about querying the database in an efficient way. And Quadrant provides us the way to do it. Okay, so how would we integrate that with Quaterion? We, of course, need to set up a Quadrant database. That is fairly easy because we provide some Docker images. And we can run it using this command. This is fairly easy. The easiest setup will just create a database on your local machine and expose the HTTP API on port number 6333. And then we can just query using curl to see if that works. And interacting with Quadrant may be done using curl or Postman, or actually any HTTP-based based client. But we also have a Quadrant client that under the hood uses both HTTP and gRPC. What is also great about Quadrant is that it's not only based on mathematical vectors, on embeddings, but also provides a way to put some payloads, some objects coupled with a specific vector. So let's imagine you work in e-commerce and sell clothes. If you just have a photo of a particular piece of cloth, you can just assign a description of the fabric, color, available sizes, I don't know, a category that this particular item belongs to. So many different things that cannot be simply put into that embedding. So we also provide a way to put those payloads and to filter by those payloads, which is also quite interesting, because if I wanted to have a car which is similar to the one that I have on an image, but with a different color, then it's pointless to just display me a list of all the possible colors in the search results. So this is really cool. And Quadrant is stores the data in so-called collections. So we need to create one also by calling the proper API method. But we are going to be using Quadrant client this time. So we need to create an instance of this Quadrant client and then create a collection with a specific name and a vector size, and this vector size is exactly the same like the one produced by our network. We also need to define the distance functions, so the way how those vectors will be compared to each other. And in our way, that is also quite popular way, we are going to be using cosine distance. There's also sometimes Euclidean distance is also used for that. There are also some other choices as well, and that's it. This is going to be created almost immediately, and now we can just upload the points. This is also quite easy because by using upload collection methods, we can provide those embeddings which were created by our neural network, and the payloads if we have any. That's just optional. So if you have any payloads, we can provide them, but if not, they may be simply omitted, and that will be also fine. And now, once we have our collection created, it will contain all the embeddings for all the cars from our database. We can just start querying them, but no longer using this naive linearly scaling approach, but with approximate nearest neighbors, which is sublinear. So retrieval of those closest points is way faster. And that's also fairly easy with Quadrant client. We just need to call the search method, provide the collection name, the same like we did for creating that collection, and query vector, which is an embedding created by the same network, and that will be used for this approximate nearest neighbor search. We can also provide some query filters that will filter based on the payload. So let's say if I wanted to limit myself only to a specific color of the car, that's also doable. And we can also return this payload along with each vector. And here I decided to use just top 10 examples from that collection. So the closest 5 points that we had, and that's it. What's worth noting is that Quaterion and Quadrant are separate projects. You don't necessarily need to use both, but if you decide to do that, then you get really cool end-to-end processing, because we started with Quadrant and we saw that there are some typical problems that our users fall into, just because the similarity learning is a fairly new approach, and classification and regression, solving classification and regression with neural networks is quite old, and we all understand how it should be done. But with similarity learning, there are some other problems that may occur, and we try to solve them. But it doesn't necessarily mean you need to use both. But we strongly encourage you, because as you may see, it allows to build a fairly simple pipeline within just hours, instead of spending a lot of time on creating that from scratch. And you may think of Quadrant as some kind of database similar to, I don't know, MongoDB or MySQL that you are already familiar with. So you just set up a database, put your points, and then query them from any single device you want to query it. So this is fairly simple. You don't necessarily need to build an index within your notebooks, because that won't let you go into production that fast. But with Quadrant, things are way simpler. So definitely that's the way to go if you want to perform the neural search within hours, not months. And that would be it. Thank you very much. Hope you enjoyed that. Hope we have some questions and some time left for answering them. Basically, would be happy to discuss anything you have in mind right now, or please just feel free to reach me using my my social channels. Thank you very much.
Yes, sir. Thank you, sir. Sir, before we proceed to answer the audience's questions, I would like to request the audience to fill in the feedback form. I'm just going to launch the feedback form. Please do participate in it. I just launched the poll. Please do participate in it. Sir, parallelly, we can go with the Q&A section. You can access the audience questions in the Q&A section, sir.
Sure. Yeah, let me just go through those questions. Okay, so the first question is about securing any image search. So if a doctor wants to search a tumor with neural search, how does open neural search unstructured data and be relevant and accurate? Okay, so about securing the image search. This is also quite cool if you use similarity learning, because as you saw, it can be divided into two separate processes. The first one, creating those embeddings with this pre-trained network, and another one for fine-tuning that network. So, okay, in the training phase, you need to have both, but if you wanted to, let's say, create a piece of hardware that would be specifically designed for the doctors, it could have this original network just built in, so it will just produce this initial embedding, and then this initial embedding will be sent to I don't know, cloud service. But just by looking at the embedding, you are not really able to come back and create this original image. So this is fairly easy to be safe in terms of securing some sensitive information, because we can create those embeddings on the edge and then send those original embeddings to be then pre-processed a bit and used for this comparison. So this is fairly simple. Hope that solved that answered that question. Okay, another one, which is about comparing Elasticsearch with Quadrant neural search. Basically, we are quite similar, to be honest, but Elasticsearch is mostly focused on this of methods like keyword-based search or faceted-based search. That's also cool. You cannot actually put everything in form of vectors. Actually, you can try to do that, but it is way easier for your users to also use some additional filtering criteria. And Elasticsearch does a great job in terms of keyword-based search. And they also expose this vector search capability, but this is a bit slow comparing to Quadrant. I have to admit, we have some numbers, but basically this is just not designed to support vectors at the first place. They are purely focusing on this odd keyword-based search, and that is working pretty well. But yeah, if you want to start searching for vectors, then you definitely need a more efficient tool to do that. And Quadrant is like a good choice, I would say, just because vectors are the first citizens of the system, not some sort of plugin as they do in Elasticsearch. Okay, can we use Quadrant for real-time search from our web portal? What is the latency? At what are the infrastructure need to support a low latency search? Well, we are going to publish some benchmarks soon, so they will definitely answer that question in some specific number. I'm not really sure if I can share the details right now. Probably I shouldn't. So I cannot answer just by providing a specific numbers, but definitely the real-time search is something that neural search solves, and Quadrant as well. This is, as I said, Rust-based tool, which is fairly fast. So the latency is not an issue, and the real-time search is also possible. When it comes to infrastructure needs, we do not require you to set up like a huge machine running with hundreds of gigabytes of memory. We even encourage to iterate with your setup. If you have some specific data set, you can already calculate the embeddings and determine how much memory that will use. And the overhead generated by quadrant is not that high. We also support mmap storage for vectors, so they will be kept on disk and just loaded from disk while you perform the search. So the requirements are not that high. I would say you can just multiply your the size of your data. I mean the embeddings. You need to calculate the multiply the number of data points you have by the number of dimensions every single vector have, and then by 3, and that's like a rough estimate of how much memory you would need. But still, there is a chance to just store that those part of those vectors on disk. So that will even reduce that. One thing that I can probably tell from our benchmarks, we were using a machine with 32 gigabytes of RAM, and we couldn't really exceed that number, even though we were using like millions of vectors with around 1,000 dimensions each. So this is we are also quite low when it comes to the system requirements, and we also support sharding, so you can set up Quadrant using several different machines. It doesn't necessarily to be launched on a single machine, so that shouldn't be a problem. But just to answer your question, that could be determined if we knew the number of vectors and the dimensionality of the vectors you want to have. But latency shouldn't be a problem at all. Okay. Well, the question is, how does the global technology applying in human body interconnecting system to provide data segmentation modify the optimizing overview in metaverse controversies around the area to initiate RPA consolidation in an innovative pathway? Well, I'm sorry, I cannot answer this one. I'm not an expert, and I don't want to pretend being an expert in that area. But that's pretty interesting question. Unfortunately, cannot tell the right answer. Sorry about that. Okay, fine-tuning means increasing the precision of the picture. No. Fine-tuning is about changing this original input of the network, so it's just closer to the target. Fine-tuning is not necessarily intended to be only used for similarity learning, but you can also fine-tune a different network for, let's say, classification. You can take an existing network, put different targets, and fine-tune it to just match your data better than initial. So fine-tuning is like another training process done on already trained network. That's it. Is this type of transfer learning? Yeah, sort of. Yeah, we are transferring the knowledge from one data set to another. So yeah, that's surely a transfer learning method. Okay, if not, how we can employ transfer learning? Yeah, this is a transfer learning. So the answer is yes. So it's also answered. Okay, is it possible to append new information to already trained model? If yes, how? This will avoid retraining time. Of course, we have already done it. So actually, we appended some new information to an existing network by providing this head layer, and we appended some similarity information from different samples to the already trained models. So that's where those pre-trained models are really cool, because we can transfer some knowledge, some existing knowledge, and append some new information. That's exactly what we did. Okay, regarding the embeddings from pre-trained model, I always thought that weights in hidden layers of pre-trained models are already trained to represent some abstract features. So I suppose we can use them directly to calculate vector distances between embeddings of arbitrary pictures without fine-tuning the model. Am I wrong? You are not wrong. That's true to some extent. The thing is that we always train our models on some specific training set. We are still far away from AGI, and I won't expect it to be finished until the end of this month, and at least, but also in the couple of years from now. And basically, if you just create the model and let's say you train that on ImageNet or even some better quality data set you collected, then it's not that easy to use it directly on a different area. Let's say if we train a model that will be recognizing cats, chances are it won't be capable of recognizing tumors on medical pictures or any kind of thing that it wasn't trained on. It will be able to capture some regularities in the data. I mean, those smaller shapes, I believe, but doesn't necessarily won't be necessarily able to like generalize over this training set, the set of classes or set of images it was trained on, because it has never seen it. But in that way, we are just reusing those let's say low-level features in order to just tweak the output. So that basically we could use those original embeddings for sure, but that's something that I presented on the screenshot from the results of the fine-tuning. That worked to some extent, but didn't necessarily work well for the cars and finding some similarities. Okay, there is dense vector support in Elasticsearch, where you could use their cosine similarity function to compare query vector with indexed vector. I am assuming neural search supports much more than this. Well, as I said, you could. Elasticsearch supports dense vectors, and definitely you can use it. There is also another feature which is quite unique for Quadrant, because let's say you wanted to combine this additional filtering mechanism. So you provide a photo, let's say, that is converted into the vector. So actually you provide an input vector, but also some additional filters. So I want a red car because they are faster. And if you do that, then there were two strategies available on the market. The first one, which is pre-filtering. So your filters will be applied to your data first, and then the vector search will be performed on the subset of your data. But let's say if I only store red cars, then I will have a list of all the IDs from our database. So potentially that will be linearly scaling, and then apply the vector search on those IDs. And that may lead you into the trouble, because you will be still performing a full scan. But there is also another strategy, like post-filtering. So we first of all perform the vector search, and then use those results to select only those ones which are fulfilling those filtering criteria. And there is another drawback here, because if we want, let's say we wanted 5 top examples, also similar to the provided vector, but also fulfilling those criteria. Then with post filtering, there are some chances that those top 5 entries won't fulfill any of those criteria. So the result list will be empty. So the strategy is like, if our user wants 5, let's select 20, and then hopefully select 5 that fulfills the criteria with the highest score. That also doesn't necessarily work well in all the cases, because if we have like very rarely occurring, let's say, category, a specific color of the car, which is not that common, then we can probably select only cars that are similar in terms of their shape, but not necessarily in terms of the color, even though if we just scan like 10 times more items than our user expected. So there was an issue. And what makes Quadrant, I'm not really sure, just to answer the question, I'm not sure about what specific strategy is used in Elasticsearch. I expect one of them, or maybe like a combination of those two. But in Quadrant, we have incorporated that directly into the vector search phase. And this is like a unique feature that nobody else has. So if you provide a query and some filters, you traverse some sort of graph, and we just select the matching rows in the same phase. So we are able to return you exactly the number of entries you wanted to have. And we don't necessarily need to have like a full scan of all the items. If that occurs, that you will provide a category that every single item belongs to, what may happen with prefactoring. So so neural search support in Elasticsearch in Quadrant is somehow similar, but we have those tweaks which makes us way faster. I really encourage you to have a look at our benchmarks when they are published, hopefully next week. So you will see the difference in terms of the latency, requests per second that it can handle, and also the precision that it may offer, because even though under the hood we use a similar method, that doesn't necessarily mean we receive the same precision. But really encourage you to have a look on our Twitter or anything, any other source, because this is going to be published soon. Okay, the case may be that we can consider that cars are similar to each other and they are different from bikes. Cars of given brand are similar to each other and they are different from cars of another brand. So I feel the definition of similar pictures matters. Yeah, it matters a lot. That's definitely the case. We need to, well, maybe I oversimplified the creation of this data set a bit, but still, if we provide less data than for classification, that has to be good quality data. Because if we just provide like a low quality data, then we will end up with some random vectors being assigned to them. So if we annotate less data, then we have probably some more time to do it properly. And if your use case requires providing both cars and bikes, or recognizing cars from different brands, then definitely you need to do that. But that can be done. You can also use this another strategy of providing pairs of examples. So let's say car of brand A and car of brand A, but different types are similar with a score 0.5. And if it's exactly the same car but with a different color, then the similarity is 1.0. So we can use this different strategy, and that will allow, that is like more robust to those possible scenarios, but also way complicated if you need to provide the data set. But that's also doable depending on your use case. If your search engine is going to recognize brands, then definitely you need to do that. But in our case, we just wanted to like have classify some different groups of cars instead of specific brands. How is PyTorch and TensorFlow different? Well, there are some different interfaces. I personally come from Keras background, but switched to PyTorch at some point, and I like it more, to be honest, because TensorFlow had a bit mess, and well, I didn't like the interfaces of TensorFlow, and Keras was the solution. I think that's currently it's like a preferred way of running the experiments. But PyTorch has, I would say, a better community, and that's why I've chosen to do it. But probably you can just recreate any network in any of those two. So there should be much differences in terms of functionalities, but only in the way that you need to implement them. Okay, well, what will be the loss function used for text-related similarity search while training data? It can be also triplet loss. There are some various loss functions. Please just see our website, quaterion.quadrant.tech, where we describe this a bit more. But triplet loss is also fine. You can use it. There are some issues with every single loss function, but just as a starting point, triplet loss it's totally fine, and it doesn't really matter because we are not using text at the end, but we are fine-tuning model that works on embeddings. So, well, at the end of the day, it's just an embedding, so it's a vector. nothing really text related. So unless, well, as long as you are able to create those embeddings with some network designed for text, that is pretty fine. Doesn't really matter. Okay, in your dataset, values of mean and STD appear to be half of each other in value, which look odd considering deviation. If I'm to ensure my output holds have some confidence level in NLP, how and or do we add the confidence level of my output? Well, basically, this is possible to be added. We have also another tutorial describing how to add the confidence level. So that was the second part. Please just go to our website, and that's pretty well described. But this is possible to be incorporated into the existing stack. If you want the confidence level, that's fine. When it comes to the mean and STD, this is just taken directly from the ResNet training process, because those networks trained on ImageNet typically normalize the images. And that was like taken directly from the ResNet process, because the original ResNet was trained using this mean and STD normalization. And we also had to do it. That's the only reason, but that wasn't chosen by us. Okay, I'm still unable to connect the dots on how triplets are created and triplet loss is calculated. Okay, so I decided to use these groups. So then this triplet loss just takes all the groups and combine the example, creates some triplets out of it. So there is an example, a positive example, which should be close to it, and the negative example that should be far away from this anchor, from this embedding. And the thing is that Quaterion automatically under the hood just prepares those triplets. If you provide those groups, and that's it. And how triplet loss is calculated? This is like a distance. Well, our network is like punished if it's close to the negative example, and rewarded if it's close to the positive one. And that's the thing. This is fairly simple if you just look at the like equation. Please just feel free to reach me out. We can discuss it one by one, but we have plenty of other comments. But this is fairly simple, and Quaterion automates it, so it just creates all the triplets for you automatically. Okay, please share code as well. Of course, this is shared. This is part of our examples, but I will also make sure that this notebook is visible, as well as the slides that I've shown. Okay, could you please elaborate on triplet loss? Well, I already done. So if you have any other questions, please just feel free to write me a message. Maybe that's also a good idea to have a longer session about different loss functions that are available for similarity learning. I would be happy to discuss that. And how many layers? Well, I would need to look at the ResNet 152 network that we used. I'm not sure, and I don't want to pretend I know. If you just look at the paper describing ResNet or the source of the source code, because that was taken from Torch Vision, so this is also publicly available. We just frozen all the layers except for the last one. So the full ResNet part of the ResNet that we used was frozen. Okay, how to relate original to tune? Please explain. Okay, so this original network was creating some sort of embeddings, but based on this ImageNet. And we in this image I presented, we show the like top 3 results returned. I mean the closer examples from our cars data set that were retrieved by comparing those original embeddings. And how to relate original to tune. They were just top results returned by both networks, the original one and the fine-tuned one. So this is like a graphical way of showing that worked as expected. But there are also some other ways to calculate how those are closer to each other. If we have some sort of ground truth, that would be doable. Are we comparing embedding while prediction? Yeah, that's the thing. We have this embedding created, and then during the prediction, we calculate the distance between two different embeddings. So that's how the similarity learning works under the hood. We compare the distance between embeddings, and please just think of embeddings as if they were some geo coordinates in some sort of space, like latitude and longitude may be thought as a two-dimensional vector. And if you calculate the distance between two different points in space, the latitude and longitude, we can have this distance between them. And that's the same thing here, but the space is way higher dimensionality. Does quadrant support audio search or use spectral analysis for audio search? We actually, well, the answer is yes and no at the same time, because basically we do not assume anything about your data. You need to prepare a network, maybe pre-trained already or just created by you, that will be producing some embeddings. And that may be an embedding of the text or audio signal or image or anything you want, actually. If you are able to create a network for your specific data type, you are able to create this, to use those created embeddings and put them directly to Quadrant, which acts as a database for selecting the closest points in a space. But that doesn't necessarily mean you, well, we do not assume anything about the data type you use. If you are able to vectorize your audio signals, that is fine, but we do not use spectral analysis because we do not assume this is an audio signal. That may be like incorporated into your neural network if you are able to use those spectral components. That could be doable or maybe even valuable, but Quadrant doesn't really assume what you put in there. Does Quadrant's database supports numerical and range filter, category, wise filter, location-based filter as well? Well, actually, all of the mentioned ones. You please just see our documentation. Those filters are all supported. So if you want to select some vectors which also has a specific value of a particular attribute, that's also doable. Does Quadrant database supports numerical? Okay, so that was already answered. Why distance cosine is written? Well, actually, you need to select how your points, how your embeddings are going to be compared. And there are several distance functions. The easiest one and the most popular one is Euclidean distance, also called L2. But basically, cosine is like a typical choice, the most popular, and that works well in most of the cases. So that's why we used cosine in that example. And distance cosine distance is an enum exposing all the supported distance functions in Quadrant. So cosine is one of the values available in that enum. What is the latency of Quadrant when there are around 100 million vectors to do ANN search for a given query? Do you have any comparison of results to other DBs like Milvus Elastic? We do, not necessarily for 100 million vectors. We are still working on those all those benchmarks. Well, this is like a really heavy setup. If you have 100 million vectors, then definitely that has to be spread across several machines, I believe. We do not have a benchmark directly, especially for that high numbers, but we will publish the benchmarks for some for the data set consisting of 10 millions, for example, pretty soon. So just stay tuned, and you will definitely have a comparison. And yeah, we compared to Milvus and Elastic and some other engines as well. Any ideas on combining search and classification into one system? Yeah, I already mentioned that, because KNN is actually a classification algorithm. This is fairly simple because we just find, let's say, 10 nearest points, 15 nearest points, and then by simple voting, we select the most probable class for a given example. So of course, this is a valid strategy. Let's say if we were using Quadrant, you could easily select, let's say, 10 closest examples, and then select the top class, most common class from those 10 examples. So that's fairly easy to be implemented. It's not like built-in, because there is no information about the class in Quadrant if you do not provide a payload with the class name. But that's also doable if you are able to provide the class for your training set that is sent to Quadrant. You can easily do it with KNN, and there is a huge advantage of KNN comparing to some other systems because it's easily interpretable. So it's like an explanation by similarity, and if you just can go back to the original examples, then you can simply tell, listen, we selected class A because that was similar to those examples from in our training set. So this is doable, and this is like a really good way to have a system supporting classification if you want to have one. So Quadrant search is better than Google search, or are we talking about two different technologies? Well, I should tell you that we are better, but we are probably not, because we are just exposing a piece of technology. I believe you can build a better search mechanism than Google does for a specific sub-area. This is quite a common example. I'm not sure if you feel the same, but I feel like the search quality has decreased in the recent years. When I was trying to find something in my in early 2005, that was way easier because there were a lot of blogs created by some passionates around different topics. But right now there are a lot of advertisement and websites like optimized for SEO. So that's the thing. If you have like a specific area, then probably you can build a better system using Quadrant. And actually the approach that Google search uses is also based on neural networks. I think that was enabled for all the languages, at least for many of them. So if you send a query to Google search, it's not keyword based. They do not compare the text only, but they vectorize it using some BERT-like networks, and then use it to find the closest point. I'm not sure what they use under the hood, but basically the idea is the same. If you can vectorize anything, something, then you can find some similar examples. And this is a completely different technology. I mean, Quadrant search is like, think of it as some sort of database. So MySQL or PostgreSQL-like database, but for a different data type. So not for relational data, but for some vectors along with some additional attributes assigned to them as well. Okay, Quadrant use C, C++ search engine in the background. For instance, Elasticsearch is Java JVM based. No, not necessarily. We are Rust based. Yeah, Elastic is Java JVM based, but we are Rust based. So that makes it a bit better in terms of performance, but also memory safe. And that's the property that we love about Rust and Rust-based applications. And another thing is also about that, does Quadrant use C, C++ search engine? No, we are Rust-based search engine. We actually do not use any search engine in the background. We are the search engine. Quadrant is a search engine on its own. So Quadrant search is better than Vertex AI. I'm not sure. We haven't done this comparison, to be honest. Yeah, it's quite hard to benchmark to Vertex AI. Well, every single system that we create typically has some sort of hardware constraints. So if you create a simple website, you don't necessarily buy a fully fledged cluster of database machines running your, I don't know, Oracle database instance, because you have a WordPress based blog. And Vertex AI is a SaaS, works in a SaaS model. And there are like 2 or 3 systems that works in the same way, which are vector databases. But Quadrant runs on your, right now it works on your hardware. You need to provide the machines and run Quadrant on your own. We are working on the cloud version as well that will be available, but we cannot benchmark to when we start run Quadrant on a specific hardware, we cannot benchmark it to cluster of Vertex AI that may be using like some heavy machines with hundreds gigabytes of RAM. So I cannot tell it's better or not. We are just open source, and that's a huge advantage because you can just start using that. And in Vertex, you probably have some free trial, but that's it. In Quadrant, you can experiment on your laptop and then move those computations into cloud or on-premise servers. In Vertex AI, you pay from the very beginning for using that. Okay, can you share the PPT? Not necessarily. I can share the PDF if that works. I can export both presentation from the beginning and the slides from Jupyter Notebook and export them to the PDF. That works pretty well. Okay, so this is done. Is Quadrant database production ready? Yeah, we are. Basically, we have some adopters that are already using Quadrant in various areas. Definitely encourage you to join our Discord because there are many passionates of vector search using it with Quadrant for many use cases. So if you need a spark of inspiration, our Discord is a way to go. And we are production ready. We do have the distributed deployment mode available. Still, this is not 1.0 version, but we try to keep backward compatibility between those major versions, so you are able to just start right away. I would say we are production ready for sure. And that was it. I see there's no other questions. There were like 41 questions already. Thanks a lot for any of them. Really encourage you to stay in touch. If you have any questions, would like to discuss how to set up vector search in your case, or if that's feasible, please just feel free to reach me anytime. Thanks a lot.
Hello, sir. Hello.
Hello. Yeah, I'm there.
Sorry, sir. There was a internet interruption. Really, thanks a lot, sir. It's great that you are patient enough to answer all the questions. And
that was my pleasure.
Yes, sure. And from the chat section, from the interaction, I can see that our audience had absolutely loved the speech. Thank you, sir.
That's really cool.
Yes, sir. Thank you, sir. Also, on behalf of Analytics Vidhya, I'd like to thank you very much for your time and your wonderful session. Hopefully,
perfect. I really enjoyed that as well. May I have a question?
Sure, sir. Sure.
Because some people wanted to have this PDF or PPT version, or actually the slides and the notebook that I was sharing today.
Yes, sir.
I think
sure.
It would be great to just put a link to the YouTube description. Can I just send it to you? And can we just put some links in the video description of that session?
Sure, sir. Sure. Please send it to me, sir. How do you like to send to me, sir?
I think email would be the best choice.
Sure. I'll send my email ID through to you, sir, in the chat section.
Perfect. You should have my email address. So hopefully, yes, we can reach somehow.
Sure. Please send it to me in the email ID, sir, so that I'll request the uploader to put the video link, like PPT link, in the description.
Okay, cool.
Really, thank you, sir. Thanks a lot, sir.
Thanks, you too.
Yes,
hopefully hear you soon.
Sure. Hopefully we can conduct more sessions with you later.
I also hope so. Thanks a lot. Bye.
Thank you, sir. Bye, sir. Also, for the audience, thank you for joining. I have posted all the useful links in the chat section. If you want, you can use these links Also, we'll be back with another DataHour session tomorrow. Hope we can see you there. Thank you. Till then, bye-bye and happy learning.